Ses. Ses. Fred? Yeah. We have 3 people, no, 2. Also, viewers on YouTube. 8.
No,
Why is the setup like both? Is everyone going to avoid sitting on the same table?
difference is turning it on now or turning it on in 2 seconds or something. I guess this way you could actually try it out, the audio.
Did you open the Windows intentionally? Sorry? Did you open the Windows intentionally?
Yeah.
Okay, so I think there are both.
I can help with that.
I'm sure it is. Sure. This will be very like one specific piece, but I don't know about chat first. I need to chat.
Probably you.
But it's fast.
Getting clean was recommendation.
Wait, that's not good.
So Dale says, I'm not joining audio, right? Is that the idea? I'm not joining the audio.
No. Sound is working.
Excellent.
Share your screen.
Right, I'm going to move this.
Logo.
This two.
This is a difficult part. You can slow down. I guess the fast one was like here with this and stuff.
Why?
It's up.
It's a kind of long manager for this thing. Every navigate like
Oh, but we need to turn this on, right?
Okay. Let's put something about this. Yeah.
So I gave the one talk in the lecture, so now I have to give the lecture here. Right?
Why is it so
Yeah.
makes no sense.
So that's what I was thinking. We don't record this, so I can speak freely.
Okay.
Yeah, I can cut these pieces
It's going to be controversial.
No, I meant the whole talk, but
if you want.
I'd,
It's going to YouTube.
yeah, I mean, I realize we have no control over it. I mean, someone is going to record it themselves on YouTube or something,
Yeah.
right? But I mean, it's all a little bit preliminary, so maybe it's better if it's not recorded.
Oh.
Also, Clement can't make it, so
Ah,
better punish him for not coming showing up.
okay. We don't have any announcements.
Well, we do. So Nathan is starting an internship with Jules and I for the spring, summer, until the end of August. In time theory, but for a concatenated language.
And we should also announce yesterday's launch of the first workshop, Transactions in Category Theory, which will take place on Monday, the 2nd of June in Royal College 512 and online.
Just for my birthday.
If you
It's
want
very
to
nice.
chuck us a talk proposal, send it to me and Jim.
Is it a contact?
Well, let's put it this way, at the moment, it's so random. But if we suddenly discover that we're extremely popular, we'd like to figure out what to do about it.
So obviously I'm very supportive of this, but I'm also, it says on Zulip that it's the first international workshop, which I highly doubt.
It's not the first international workshop, it's the first international workshop transactions.
I guess other announcements. So I put something on Zulip this morning about thinking about what to do with all the money we have. Just to point that out. I mean, let's not do it now because then I won't have any time for the talk. But
Total is over £4,000.
yeah,
This is our booty from SPLP.
And the MSP, like every team has got a data to come from the department to organize team building.
Something going back to Butte.
Butte was more expensive than 2K, but we could consider something like that. And maybe not so many days, and maybe not so many invited guests.
Good enough colleagues.
Yeah, so I just want to make people think a little bit about it.
Yeah.
I also had a feeling that I had another announcement that I wanted to put on Zulip, but I completely forgotten what it was, so probably wasn't important.
Did you want to announce that you were going to fix the aspect ratio?
Okay, that's actually very bad. Let's fix that. Yeah.
Yeah, I think the only other thing is a reminder that on Friday afternoon, we have the presentation from the Chancellor's Fellows for MSP.
All right, so that's very nice.
Yes.
Yeah.
It might be online.
It's online, yeah.
Yes.
We could consider to book a room to watch it together.
Have a watch party.
I mean, they won't know that because they will be online. Right?
I'm not sure I'll make it. Might have a meeting that time. Just maybe one question is there a strategy with the quantum? Because there's quite a few quantum. Is that an area we're moving into? Are we just responding to who are the best candidates?
It's purely, I don't know what the shortlisting, but the listing was pretty based on who the candidates.
Okay, so it's
Yeah,
purely
just the best candidate. And I don't think we have, I mean, in my mind, we have one quantum candidate, which maybe you think is already a
I
Oh,
lot.
can't remember
But
the exact list.
Yeah, I mean,
Just,
yeah, before you
I guess also a final announcement. Types deadline is next week. Calco deadline is tomorrow, I think.
MFPS is a bit
It's the same.
later.
And it would be nice to have some local submissions to types.
Yes.
And
It's 2 pages.
2 pages, yeah. And we if people are worried about the registration fees, we could work it out if it's local. But okay, should we start? Yeah.
Sure.
So I'm curious who's online, but maybe I'll find out afterwards. Excellent. It's not too many people. Good. So I'll just try to tell you it's a little bit of new work together with Liang-Ting Chen and Chu-Chen Tsai, who is Liang-Ting's research assistant in this lovely building here in Taipei. So it's a little bit of new work, but it's also a little bit of just recapping and what I think could be cool to know about how to do type theory and type theory, right? So why would you want to do it? Well, there's a bunch of M's. So you might want to do metaprogramming, which would mean that you somehow manipulate terms inside of your programming language, right? You might want to do meta theory in a mechanized way, in the sense that you actually want to use a proof assistant to be sure that you haven't left out one of the 10,000 cases of your induction over the structure or something like this. You might just be mathematically motivated in the sense that it's an interesting mathematical structure, so it's worth studying for its own sense. Or for us, it was mostly looking for interesting and kind of non-toy examples of using advanced inductive types. So I'll talk a lot about this for the rest of the talk. I also thought I had another reason. Oh, yes, I just wanted to say that, so what I'm talking about here is more on the kind of formalizing meta theory side, or reasoning about type theory rather than implementing type theory, right? So I don't necessarily mean how do you get an efficient evaluator or an efficient type checker or anything like this. I just want to study type theory as an internal object in my other type theory, for the reason I'm saying here, right? So let's warm up with just doing simple type theory, because this is very easy, or relatively easy. So this is the recipe you probably follow. So we want to represent the well-typed terms of a simple type theory inside of our favorite type theory or proof of system, whatever it is. So I would do it this way. I would start by defining what the types are. So saying that there is some kind of base type, let's say n for the natural numbers, and I'm closed on the function types. So whenever I have two types, then I have another type called A arrow B, right? And I do this inductively, meaning that I want the smallest type that are closed under these constructors, right? So I want to have a constructor for the natural numbers, and I want to have a constructor for A arrow B whenever I can construct A and B. And then after I define the types, then I can define what it means to be a context by basically saying that a context is a backwards list of types representing the types of the variables in my context, right? So I either have an empty context, or if I already have a context, then I can extend it with one new variable which has this type, right? And it's kind of convenient to not use lists, but to use backwards lists so that things really grow on the right side. But this is, of course, just for convenience. Okay, so if I have these concepts, then I can define what it means to be a well-typed term in a given context of a given type. And again, I can do this inductively. So say that variables are terms. And what's the type of my variable? Well, I specify my variable by talking about an index in my context. So I have some index that says that S is at position 5 in my context. Then variable 5 has type S, right? And I can throw in terms for 0 and successor. So 0 is always a term of type n in any context gamma. And if I have a term of type n in context gamma, then the successor of that is also a term of type n in context gamma, right? I can throw in a term for the recursion operator, the eliminator for natural numbers, which says that for any type S, if I have a term which I want to stand for 0 in my type S, and if I have a term that I want to stand for the successor of type S, so in an extended context, so I have access to my gamma, I have access to my n, I'm currently trying to eliminate suck of n, right? And I have access to the recursive call on n already, right? So I have extended my context with two things. So I have to give one of these. Then the recursive says that for any term n, I can get a term s. Okay, and then if I have two constructors for function types, so I have lambda, which says that, well, if you have a term of type t in a context with a variable of type s, well, then you can abstract that variable to get a term of type s arrow t in context gamma. And one way to formulate application is to say, well, we have an inverse to this function. It's saying that if you have a term of function type, well, then you can apply it to the variable, so to speak, and get a term of type t in an extended context. So of course, you could formulate this the usual way, where you say, well, if you have a term of function type and you have a term of type s, then you get a term of type t, right? But after we've defined substitutions, then you can derive that from this one. And the nice way of formulating it this way is that it's now very easy to formulate, for example, beta reduction, right? It's just saying that if you first do lam and then you do up again, you get, sorry, the other way around, I guess. If you first do lam and then up again, then you get where you started from, right? And the eta law, which says that everything is a lambda, is the other way around. If you first do an up and then do a lam, then you get back to where you started. Okay, so once you have terms, then we can also define substitutions between contexts. It's basically lists of terms, right? So the substitution into a non-empty context should give a term for every element in this context in the original context. And after you define substitutions, then we can define the reduction relation, saying that this term should reduce to this one. So for example, up of lam should reduce to just the original thing, right? And of course, you can have different choices. So this is basically De Bruyne indices for the variables, right? I mean, pick your favorite scheme here if you want. Doesn't really change that much. But this is a kind of straightforward recipe, right?
Substitution.
Sorry?
How do you define substitution for define substitution for the last x? And then vanishes in the
So how do I define the normal application? You mean? No?
No, how do you define substitution?
Right. So I'll first just define what it means to be a substitution, and then afterwards I define how the substitution acts on a term, right?
Right.
And I guess you're asking, how does a substitution act on up? And we'll see this for pi types later. It's even more complicated. But basically, if you substitute on an app, it's still an app, right? That doesn't go away. So you substitute under the app, but you lift the substitution to act as the identity on the last variable.
Yeah, but you've got a substitution which is replacing the s.
So if I have a substitution from gamma to delta, then I can lift that to a substitution from gamma comma t to delta comma t.
But it was in the other direction.
Yeah.
So that's
Like the
already
S disappears when you're pushing it from.
Okay, I don't.
So you're coming along, you've got a mapping, you've got gens in app.
Right, but then I have a substitution from here, right? If I start with an up.
Yeah, and you want to push that substitution to the argument.
Right, so I can always forget about the last the term for s, right?
Then you won't get the right thing to apply.
Isn't that scary?
Yeah, okay, why don't we,
Okay.
we'll postpone it till we have this for pies, because yeah. Okay, so my claim is that this is easy and very well understood and no problem, and no one is going to ask you any tricky questions about how substitutions act on apps.
So that's my question, but what's the motivation for presenting app this way?
It's so that I can very easily say what beta and eta is by just saying that app and lam form an isomorphism. Right, so we're not going to see how it works for app later, because later we're just going to say how a substitution acts on lam, and then by the fact that it's an isomorphism, you can derive what it should do on app. So I guess I'm kind of bypassing the problem. But I mean, of course, when you use that, you do something. I don't know what you do right now.
I just thought you cover the more traditional app.
So if I have a function, one of these, and I have a term of type s, then I do up of my function. That's going to be one of these things. And then I substitute my top variable for my s. Right?
I guess the real question is why there is no term constructor for the action substitution.
Right. Yeah, that's a good question, and the reason is that you can define it, right?
Step through with presence, yeah.
Right. So the reason was that I thought you could define it. But okay, let's move on to the dependency type version, I think, because there will be a term. Maybe I'm just wrong and you can't define it and you need to actually add in the substitution here. So the thing I wanted to point out was that if you do it this way, so you define substitutions, then you define the reduction relation you want, then this reduction relation just tautologically is just the relation, right? It has a priori nothing to do with real equality. So if you actually want to treat equal things as equal, then you have to keep track of this yourself, right? So I'm claiming that app of alarm is the same as doing nothing, but when I define my printing function that takes one of these terms and produces a string, then I have to be really careful that I really treat these things the same, right? So to summary what we've done, we started with types, then from types we derived contexts, from context we derived terms, from terms we derived substitutions, and from substitutions we derived what it means for terms to be equal, right? If we try to do this again for dependent types, then we have the same kind of ingredients, but we can't really start with types as our first building block because types only make sense in a given context, right? If I'm telling you this is the type of vectors of length n, then this only really is a type if n really is a natural number. If n is a Boolean, then that's a nonsensical type, right? So before we have type, we really need contexts. But of course, we can also have terms actually occurring in our types, right? It's dependent types. So before we have types, we better have terms as well. And then if we have these things, then we'll have substitutions in our types. And we want to be able to replace equal things for equal things in our types. So we better define equality before we can really get started on the types, right? And of course, the types are actually occurring in the context still. So these two things kind of depend on each other. And if you think about it, then basically everything depends on everything else, right? Typically, I don't think you have the notion of an equality of context. So you don't really have as many things leading into equality. But otherwise, it's basically a complete graph. So we just need to define everything simultaneously with everything else, and that's just life in a dependent world, right? This nice stratification of types first doesn't work anymore, just because we have more interesting types. So that's just something we have to live with, right? So some people have tried to do this. So to me, at least, this history kind of starts with Nissa Danielson's paper from 2006. Which actually, when I looked it up, was published in 2007, but it's from Types 2006. And he did this in a kind of precursor to Agda called Agda Lite. And he used some, what you could call foundationally underexplored aspects of the system, in the sense that no one knows what these things mean. And I can make fun of this because we're going to do even crazier things in this work. So we really see it as a kind of motivation for exploring these things, right? But one thing he did do, which was kind of annoying from our point of view, is that, again, he had this explicit equality relation, right? And then he always has to prove that all the constructions he does respects this equality relation. So you could call it an instance of setoid hell, where you don't really have sets, you just have sets with an equivalence relation, and whenever you define a function out of your set, you have to prove that it respects equality, right? Which is a lot of work as a user.
I'm not familiar with the add the light one, but wasn't he also using non-strictly positive inductive families? Which is the meaning to pi times.
Possibly, not sure. I mean, I'll point out one thing that we did that he did as well, which is a little bit weird. But, so I think, again, I don't know exactly the history, but I think some of the motivations by James Chapman was to get rid of the weirdest things in this use. So he did it in Agda 2, which was out by then. And it's, I would say, foundationally more straightforward. It only uses inductive definitions rather than some kind of inductive, recursive, and maybe these non-strictly positive things. But because this is before we had some idea that it might be nice to do quotient types, it still had an explicit equality relation with a lot of manual proof effort, right? And then 2016, there was this thing in the air, which had been in the air for quite a long time, that with some inventions from homotopy type theory, you should be able to do this in a cleaner way, right? So the idea by Altenkirch and Kaposi was to use quotient inductive types, which means that not only are we introducing point constructors, so constructors for data in our type, we also introduce constructors for equalities between data in our type at the same time. And this means that all the constructions, they automatically respect this, because equality really is equality, right? It's not this relation that we then later prove we respect. And by the way the system is set up, we cannot treat internally equal terms differently. So you could say that this is a problem if you want to define your printing function, right? Because now you can't print lambda f of x different from just f. But if you're doing your reasoning about these things, then I think this is what you want to do. And the nice thing is that we don't really have to define this equality separately anymore, right? So we go from this kind of situation to this kind of situation where everything is still depending on everything else, more or less, at least transitively, right? But it's just a much cleaner situation rather than having this complete graph. It's not complete anymore. But one thing I'll try to convince you of is that there is still some kind of hell that we have to live with in this situation. So we had setoid hell in the early work, and here we have something called transport hell instead. These are terms that the homotopy type theory community uses.
Are these hells actually stopping you, or is it just lots of work?
It's lots of work, but if you have high enough pain threshold, then you can do it anyway. Right?
You can move it.
Okay, so how do we do it? So again, we define everything inductively, but this time we have to do it simultaneously, right? So we can't kind of stratify it. And if you think about how you want to set things up, it would be something like this. So we still just have a set of contexts, and then between any two contexts, we have the notion of a substitution from one to another. Types make sense in a context, because we want to know what vec n that makes sense or not, right? And terms make sense in a given context, and they have a given type, right? So we make sure that our terms always are well typed, that they have a type. And then, so this time, rather than starting with types, we kind of have to start with the things that nothing else depends on, right? So nothing depends on context, but everything depends on context. So I'll introduce what it means to be a context first. So contexts, again, are basically the same as before, right? So we have an empty context and we have an extended context. And the only difference is that in the extended context, we now have this dependency that before we had a context that we were extending, and then we just had a type. This time we have a context that we are extending, and we have a type that makes sense in the previous context, right? So we're really building up a context where everything is well formed in the scope of the previous things, right? And for now, I'll keep the types very simple, and I'll build up to them eventually and add more features to them. So I'm going to ensure that I have a base type to not make it completely trivial, right? And I'm going to call it U because I'm going to reuse this base type for in universe later. And I'm going to ensure that types, there is an action on substitutions on types, right? So if I have a type in context delta, and I have a substitution from gamma to delta, then I can pull this type back to get the type in context gamma, right? It's always confusing in which way these substitutions should go, right? And as a rule of thumb, it's always the way you don't think at first. But, okay, so I'm just saying I have this constructor, right? Because I know that I need to be able to substitute in types. Okay, so what are substitutions? So like I said, I could think of this basically as a list of terms. So if I have a substitution into a non-empty context like this, then I should have a term of each of these types. So that's what I'm substituting that variable for, right? And it should make sense in my original context gamma, right? So as a special case, if n is 0, then there are no such things, and there should be one unique substitution from gamma into the empty context. Right? So this is why it's nice to have the direction this way, because then later you can say if this really is unique, then you have this empty context as a terminal object in your category. Okay, but we're not enforcing uniqueness just yet. We are saying there is a thing which goes from any context into the empty context, right? Which is giving a term for every variable in the empty context, well, none of them, right? Okay, and then we have a way of extending a substitution. So if I already have a substitution from gamma to delta, and if I now want the substitution from gamma to delta with one more variable, well, then I should give a term of that type A, but for this type here to make sense in context delta, then I have to first apply the substitution to the type, right? So A makes sense in context delta. That's how we're extending contexts. So if I want the term in gamma, then I have to apply the substitution. So everything makes sense in scope of the previous thing, right? That makes sense? Okay, and then I was already saying that I wanted this thing to be a terminal object, so that means that I want my substitutions to be a category in general. And you could try and kind of define these things by induction on the length of the substitution and so on. But for now, it's a bit iffy if you have to do this in the middle of your definition, right? So for now, let's just throw in identities and composition. So I'm inductively defining what the substitutions are. So I'm going to say that there's also an identity substitution from gamma to gamma for every gamma, right? And there's always a composition which says if I can go from gamma to delta and from delta to theta, then I can go from gamma to theta. Right? And because I have this quotient constructor, so I can introduce equalities, I can be a little bit looser about having non-unique representations of things, right? Because I can always quotient and force things to be equal later if I really have to. Although that might be part of the problems we'll see, but we'll see. Okay, so we have these kind of the canonical way to make substitutions. We make sure we have identities and composition, and we'll also make sure that we have this kind of projections. So if we have a non-empty substitution, then it should be possible to forget about what we did with this last variable. So this is like a weakening, right? And conversely, if we have a non-empty substitution, then we should be able to get a term for this last variable, right? So I'm thinking of this as my list of terms, then pi2 is really extracting the term I had last. But I need this pi1 to fix up the types, right? Because this makes sense in delta, but really I want something that makes sense in gamma, right? Okay, and then I also want to have an action of substitution on terms, just like I had for types, right? And then again, we have to use the type substitution to fix up the type of the term substitution. Yeah. Does that make sense, Sansi? Yeah, I'm calling you out because you're speaking. Okay. So this is also how we get the variables in this setup, right? Rather than having this De Bruijn indices. We are saying that whenever you have a non-empty substitution in a non-empty thing, then you can always extract a term from this thing. And if you don't want the most recent variable, then you can first do a pi1 and then you do a pi2, and that gives you. So it's basically still De Bruijn, right? Yeah.
I have a question. Would this set of substitutions only work with quotient types, or does it still work well without quotient types?
So if you set it up exactly like this, then it's very scary if you don't have quotients to have composition as a constructor, right? Because without quotients, you can't say that F composed with the identity is F, right? It's just a constructor, it's just some data. So you won't get the right equality without either having a quotient or some kind of equivalence relation, right? So maybe if you work a little bit harder and try to define composition recursively or something like this, then maybe, but okay, so that's substitution. And like we have said, we need laws, so we'll introduce them as equality constructors. It will look something like this. So what are we saying? So we are saying that, well, first of all, if you substitute, if you act with the identity, then that should do nothing. If you act with a composition, then that should be acting with the first one and then with the second one. But because of this, things going the wrong way, this always confuses me, right? And if you act on your base type, then it doesn't matter what substitution there is nothing to substitute in this base type, so it just returns U. And then we have this uniqueness laws, which says that, well, if you have any substitution into the empty context, then it's equal to this canonical one. And if you have any substitution into a non-empty context, well, then you can always split it up as saying, take the topmost variable of the substitution, and that's your topmost variable, and the rest of your substitution is the weakening of the original one, right? And finally, we have these category laws saying exactly that if you compose with identity on either side, you get this the sigma you started with, and we have associativity of composition, right? So since we have these quotient constructors, we can just introduce these as new data that gives us the right equality. So let me give you an example of where this is not as nice as you would think, right? So,
Sorry, can we go back to the previous equation? Are they all independent, or do you need some of them to type check other ones?
So that's what I want to get to now. So all of these are independent, but there are several derived equations that you want that don't really make sense on their own, right? So I'm claiming, for example, that I would want this kind of equation. So the left-hand side says this is a composition of the substitution which replaces the top variable by t, and then after that we do sigma, right? And the right-hand side says, well, I want to replace the top variable by sigma applied to t, right? So you would expect this to be the same thing, right? But unfortunately, this doesn't even type check as stated, because to make this extension of a substitution here, I want to have something which is a term of the right type where I have fixed up the substitution with this composite, right? But the thing I have actually has this type where I have two actions of the substitution rather than the action of the composite substitution. So of course you can fix it. You just have to transport along, because we have an equation between these two things, right? We said that they would be the same. So we can use the transport which substitutes equal things for equal things and put that here, right? So then we could you could state this equation like this. But now we're starting to have transports in our terms, right? And it's only going to get worse from here. And we see we also want some more equations, and most of them also need transports. So the first one is fine. It says that, well, if I weaken one of these extended things, then I get the first component. That's fine. But then to state the second thing, that if I take the topmost variable of an extended thing, I get the t. This only makes sense up to this equation, right? So you need to transport one side along this equation. And similarly, if you want to say that acting on a term t with identity substitution does nothing, well, this thing here on the left has type A, where you act with the identity substitution on A, and on the right it just has type A, right? So they, again, only have the right type up to this previous equation. And the same thing for acting with a composite, right? It only is type, has the right type up to the fact that type substitutions are equal up this way. Right? Okay, I've left myself a half in this sentence. So that's the whole definition, all of these things. And what I wanted to say with this half in the sentence was that they then go on to show that you can actually use this for cool things, right? So they prove normalization by evaluation for this type theory, for example. But in some sense, of course, the type theory you have represented is whatever you have represented, right? If you change some of the constructors, then you have a different type theory. And you can't really catch if this is capturing what you had in your head or not. But, right, so here's another example of where things don't quite work out as you want. So here's another equation that you might expect to be true. So it's saying that if I have a composite and then I take the topmost variable, well, that should be the same thing as taking the topmost variable in tau, but then applying the first substitution, right? And why would this be true? Well, look at this reasoning. So I'm starting with my left-hand side. Then I know that my tau, by the eta law for non-empty things, I could write as pi1 tau, followed, and my topmost thing is pi2 tau. Okay, and then I had an equation, this concat equation, which talked about what happens if you compose with one of these extensions, which turns this into this. And then I'm taking the second projection of this, so that's just going to take whatever is after the comma, which is this, which is the right-hand side, right? But again, this is not well-formed because the two sides of this equation don't quite have the right type, right? The problem is that the left-hand side has this type and the right-hand side has this type. And again, you can prove that these are the same and you can put in a transport. But if you do that, then these 3 lines of proof becomes 5 lines of proof. So you basically increased the size of the proof by 50%, right? And this happens all the time. So again, if you have enough stamina, you can do it. But not all of us has as much stamina as you, Bob. Okay. Right. So can we do better? And the answer is no. Thanks for coming to my talk.
Well, does it actually scale? Is it actually 50% or 2/3 of all of these kind of?
I think pretty much, because you have these small equations that you want to use all over the place, right? I mean, I think the real kicker is that not only was the proof steps wrong, right? But actually even the equation is only true up to p. So when you want to deploy this equation somewhere else, the problem hasn't gone away. You didn't solve it once. Now you have to reason about whichever particular proof p you had here, right? So what is the problem? Well, the problem is that we have type substitutions in particular, right? It's all about fixing up type substitutions that are propositionally equal but not definitionally equal, right? So what if we could arrange for them to really be definitionally equal? That would make a lot of these problems go away, right? So if we go and look at Danielson's original solution, which goes back all the way to Peter de Beer's first paper where he said that we could do something like this with internal things, then we could try to replace this piece of just inert syntax, the constructor for type substitutions, with a function that actually computes, right? But what that means is that we do not, so before we had a quotient inductive type because we were inductively defining a lot of things, and then we had some quotients. But now we also have this recursive function thrown into the mix, right? And this was one of the reasons why people were a bit suspicious of Danielson's paper. But, it's using, I mean, the system accepts it, but it's not really foundationally justified, right? Especially since the standard justification of doing induction recursion talks about having a recursive function to something that already exists. But here we have a recursive endo function from types to types, right? So all of the justification for induction recursions don't apply here. And you can kind of hack it into Agda, but the only way we need to do it is to use rewrite rules, so it's not safe anymore. So you shouldn't trust it too much, but you could see this as a challenge that we want to make this make sense, right? So here's the first attempt. We just define it as a function like this, saying that, well, if our substitution is the identity, then we give back A. If it's a composite, then we apply it twice. And otherwise, we look at all of the types. We only had one type now, so we just return that. And when we get more types, then we need to add more things here, right? So unfortunately, that's not quite good enough because it doesn't give us all the equations we want. So it does give us the equations for identities and composition, but even though you write it like this, so it looks like U acted on by sigma is U, when you look at the translation to case trees or eliminators, then this will only be true if you know that sigma is not an identity or a composite, right? So you don't actually get this as a definitional equality.
If you're defining functions now, can you define identity and composition as functions on substitution?
Yeah, I think you probably could.
And this is the way, then you can define it purely on name.
But I'm not sure if I will get all of the equations that I want.
Because I've already this function, which should be defined by matching the type, not the substitution.
Yeah, I mean, maybe, but I'm not sure if I would still get the behavior I want, because I really want it to be strict in many ways, right?
There's no point in arguing which kind of arithmetic to bring to the
Yeah. So indeed.
I mean, another thing is that U doesn't mention any variable, so it makes sense to throw away the substitution. So if you have a further Brown presentation, you never explored subterms if they don't contain variables.
Yeah, I don't think standard pattern matching has any chance to work here. I think there's always going to be disappointed. So we using these rewrite rules, we cheat, and we use overlapping patterns. So we just want them all to fire, and this is not supported by out of the box in Agda today, but you can again hack it, and I think with more work you could maybe make it work. And then we can also throw in some more convenient rules that whenever they make sense and they have a direction from left to right, right? So we know that pi 1 of such a thing should be sigma, so we might as well just reduce this to that and so on. But of course, what you have to do then is you have to manually check that this makes sense, right? If you're adding this as rewrite rules in Agda, then there's no termination checker running on your function anymore. there's no confidence checker running on your, well, there is a confidence checker if you turn on the rewrite rules. But of course, I could write down something here which made no sense whatsoever, where A of ID goes to B, and A of ID composed with ID goes to C, right? So I need to check that whenever I have two left-hand sides that are the same, then they really go to the same right-hand side, right? And unfortunately, I have to kind of do this manually.
That's what confidence check means.
Yeah. Well, local confidence checking, yeah. And I also have to be really careful about the quotients, right? So before I said that the quotient inductive types made sure that if the quotients equate two things, then all functions out of it needs to send these to the same thing, right? But if I just hack it with rewrite rules, then I have to check this manually again that I really respect all of the equality constructors, right? So again, we do this on paper. So it's not really checked by Agda, which is another reason why you shouldn't think this is safe, right? Okay, maybe I should speed up a little bit. But if there's no compute, then the nice thing is that all of these transports just disappear, right? Because everything has the right type and you don't need the transports anymore, right? And in particular, this kind of reasoning just works, right? Because there's no extra steps. Okay, so, but this is, of course, a very, very small type theory. We have one type, we have no non-trivial terms because we didn't throw in any terms of type U. So let's extend it a little bit. So we could start by actually making U into a universe by saying that there is a type EL of A whenever A is a term of type U. This is the type of elements of the code A in the universe, right? So if we add this, this should have been a green EL. It's another constructor of the type, inductive type. So if I add this new constructor, then I have to say what my function does to this, right? And the obvious thing to define is to just push the substitution. So this is the type substitution, and I'll just push it to a term substitution on the little u, right? But unfortunately, this breaks confluence. Because if I start with my substitution being the identity, well, then I could just push it in, as my rule says. And then this substitution here was just a constructor, so this doesn't reduce to anything else. It just is what it is. Or I can use my other rule for my type substitutions and say that the identity acting on anything is just anything, right? But there's no reason to think that U and U acted on by ID, two different lumps of syntax, that they would be the same, right? So this is why it's not confluent. So we have to do more work. We just have to make the term substitution compute a little bit as well. So we define this as a function, and there's some cases we can deal with, and then the other cases we just revert back to the constructor. So it's like a smart constructor. Because again, I don't think if this sigma is just a pi1 of some tau, then I don't know how that action should work, right? In terms of the action on tau, for example. So we still need to have the constructor, but we have this smart constructor that we deploy before we get to it. And it computes just enough so that things work. And note that there are no overlapping patterns here. All of these things are different. So this could just be defined as an ordinary function if you wanted. Right, and then we can define the type action as using the term action. Right. And of course, now we have changed the equational theory of these things. We have to recheck the termination and the confluence and so on. But this all works out fine. Right? And we can also prove that actually up the propositional equality, this smart constructor and the ordinary constructor agrees, right? So we can go between them. But of course, we don't have that up the definitional equality, right? Then there would be no point. Okay, let's add pi types. So this is similar to what we argued about before. So we add in a new type, which says that whenever you have A as a type, and if you have a type in an extended context, you get a type. So these should be the dependent functions from this type to that one. And then we have lambda and up, like before. And we state these two equations, beta and eta, just by saying that if you first do lambda and then up, then you get t, and the other way around, right? So that's why I wanted to phrase lambda and up this way, right? But if we now try to do the naive extension of type substitution, where we are substituting in the pieces, and then here we are kind of extending the substitution, we're doing nothing on the last variable. Then again, because we have some piece of inert data here, we'll use the confluence in basically the same way as before, right? So we also have to define this lifting recursively in pretty much the same way. We deal with the cases we know how to deal with, and then in all the other cases, we just revert to the default implementation, which is the constructor, right, like this. And then we can deploy that here. And because this computes just enough, then when we say what it means for lambda to substitute in a lambda, then we don't need array transports, right? We can just use this computing lifting. And then I claim, but it's not on the slides, that if you know how substitution works on one pair of an isomorphism, then you can derive how it works on the other pair. So whatever that does is what we do with the app. Okay, and again, we can show that kind of the smart constructor coincides with the dumb constructor, after proving that the dumb constructor preserves identities in composition. So this lemma you prove with the quotient constructors you've thrown in, right? Because it's talking about two pieces of syntax, but we're not talking about confluence here, we're just talking about things being propositionally equal. So we have more space to prove things equal. So you prove that these are the same, and then you can show that this thing is terminating in locally confluent again. And again, you do this by hand, right? To show that it really respects the quotients, you have to do even more work. So you have to, rather than just defining a single lifting, you have to lift an entire telescope and prove a lot of simultaneous things. So it gets a little bit crazy, but in the end you get back the property you want, that we really respect this equality constructor, right? Speeding up a little bit. So there's some things you can add very easily. If you want identity types, you can add them in. If you, rather than just having one universe, you want to have a whole hierarchy of universes, that's fine. If you want to have any kind of negative type, really, so like a unit type for the Nita law, that's fine. But if you add in inductive types, then we don't quite know how to do it fully without transports. So let's look at the simplest inductive type. Maybe I should try to stop quite soon. So I just have the booleans. It starts off fine. So I'm saying there is a type called 2. It has two terms, 0 and 1, which are terms of type 2. I have an elimination principle which says that whenever I have a property P, which is a type in this extended context, so it's a property that talks about the Boolean, right? And if I have a term where I instantiate this last variable with false, and I also have a term where I instantiate this last variable with true, then for every term of type Boolean, I can get my property instantiated to that B, right? So far that's fine, no transports or anything. And it's not hard to define what type substitution should be, because again, this is a thing with no variables in it. So surely it should just throw away the substitution, and that's not going to create any confluence problems or anything like this, right? So that's fine. And it's also fine to state the beta rules, which says that, well, so really there should be two of them, I've just written them as one. It says that if you apply this eliminator to true or false, then you should get the corresponding method here, right? But unfortunately, when you try to state just the structural rule, what it means to substitute in the eliminator, so I have this eliminator, I want to apply a substitution to it, I just want to push it to all the pieces, right? Then you see that one side of this equation is going to live in something like this, and the other side is going to live in something like this. And unfortunately, I don't see a way to direct this equation to say that, well, this left-hand side I could make reduced to the right-hand side, right? Even though it's talking about type substitutions. So at the moment, at least, we have to have these transports here in this, so we can't do a completely transport-free theory, right? But it's still a lot fewer transports than in a standard QIIT version, where you need a transport already for the beta rules, right? Okay, let's just wrap this up. So you can define elimination principle, so that's what it means for this to be inductively defined. It's the smallest thing, so you can eliminate out of it. And you can use this elimination principle to construct the standard model, where you interpret contexts as sets, substitutions as functions between these sets. Context extension is a sigma type, so the type of pairs. Your types are also sets where you get values for all the things in your context, and your terms are these dependent functions, right? So you get the standard model. You can also use the elimination principle to translate between this version and the standard QIIT version by eliminating into QIIT context and so on. And then with quite a lot more work by Jean, LangTing's research assistant, you can show that these things are actually equivalent. Right? So you can translate back and forth between the standard QIIT version and this version. But again, I have some kind of flimsy proof by example that if you use the version where you have computing functions, then a proof of MBE for this theory is about around 20% shorter. Right? So you do gain a little bit, at least anecdotally, if you use this rather than the other one, right? So let's just stop here, I think, because it's well time. So I tried to show that adding in recursion into your definition of type theories lets you banish a lot of the transports that arise. But we also need to do more work to actually justify why this even makes sense. Right? Stop here.
So how far along is the effort on justifying QMRTs? So someone somewhere has already justified inductive types.
Yeah, so I would say nowadays quotient inductive types are well understood. So the thing that's missing is adding in this recursive function, and then step 2, adding in this recursive endo function rather than a function to something well known already, and step 3, combining it with overlapping patterns. Right. So there's probably a few PhDs in there.
Is it plausible that the problem with Booleans would be fixed if it wasn't just rewriting, but some kind of more elaborate model checker, which could do a bit of algebraic reasoning?
I think the answer is clearly yes, in the sense that if you move to full-on extensional type theory, then the problem goes away, right?
Maybe you could augment the type checker with your own solver or
Right.
substitution theory.
I see. Yeah, I guess so.
So you could give the rules that were originally given in the QIIT version, but then also say, here's a solver. Extend the type theory. But then you're going to do that simultaneously with it.
Yes.
do things if you move to extensional or observational type theory?
So extensional, all the problems go away, right? In the sense that all of the previous equations just turn into definitional equalities. So you never need a transport. Observational type theory is interesting, and I don't know.
So in extension type theory, of course, all your problems go away, so you also solution. That's fine, you just rename it computational type theory in order to cover up the fact that this is yeah, I don't know how this plays out in observation type theory, or in that style of thing. I mean, the real problem is that the definition of is too stupid. You're responding by being clever. Just always. Yes.
But nice when you can get away with it, right?
Would you get any mileage from using some proof of relevant? Well, at some point you said, well, you've got transport along P, but if you've got two different P's, then what's the proof there?
Don't think that plays a role, because I'm already assuming kind of propositional proof relevance, right? That uniqueness of identity proofs. And I don't think making that definitional would make a difference. I mean, I could be wrong, but
So you're concerned with types?
yes, I mean, you'll notice that I never stated any equations between equations, right? I only stated equations between level 0 things.
So it's right, so it's
Yeah. You can make a setoid model, or if you're classically inclined, you can just interpret types as sets, and it would be fine.
I didn't see. Did you have large elimination of the Booleans?
I didn't, but I have a universe, so it's kind of the same thing, right? And that's not where this problem comes from, right? I mean, this particular problem of trying to avoid transport, but would be orthogonal to that. You could. I mean, it's an interesting idea to do it observationally, because you would then the transports themselves would compute, right? Much more than an ordinary type theory, and then maybe they could compute away just enough to be useful.